All right. So we're still going to be talking about annuities in this next section of material, but as you can kind of see behind me, instead of talking about future values of annuities, we're going to be talking about present values of annuities. So we're actually kind of flipping the script in this case. So before, the idea was we were making small installment payments, so we have a big lump sum at some point in the future, right? Right. For present values, we're actually putting in a lump sum at the beginning and then drawing small installments out of it as time goes on until we've bled the account dry. So that's sort of what we're dealing with here. So it's like we reversed gears in some sense. So when it comes to calculating these guys, we'll again, like we saw before, talk about ordinary annuities first. So that's in an instance where now we're making payments are being made to us at the end of whatever our periods are, be they months, years, what have you. You remember from last section. Okay, so the formula looks like this. Our textbook uses A sub n for present value. One of these years I'll remember to go look and figure out why we're using some of the letters we're using. For now, just go with it. Anyway, so this part should look familiar. We start with like the regular installment payment sitting there. We got some brackets. Notice what's inside these brackets is now kind of twisting a bit, so it's important to note the difference here. So the idea kind of looks like what we saw last time. The big difference is kind of coming out from that hole. We're making it get smaller as time goes on instead of it growing as we make more payments. But before we had the 1 plus I term in front here and we subtracted 1 from it. Now we're going kind of the other way around, but not quite. We got the 1 up front minus the 1 plus I. Note that now our exponent is going to be negative instead of positive. So you don't need to worry too much about the technicalities of that, so long as you remember that's what's happening inside our formula. Okay, so we still got the I down on the bottom. That part hopefully seems comfortable. All right, let's take a look at some examples. So first off, we want to know how much we need to put away. That's our A sub n. This is our lump sum in this instance. If we're wanting an annuity to give us $1,500 payments once a quarter for the next 12 years, okay? So in this particular example, we're told we want R to be 1,500. We need to work out our periodic interest rate and number of payments. The interest rate we're given is 10% compounded quarterly, so that would be 0.10 and 4 payments per year. That's quarters. So our periodic rate is going to be 0.025. N is going to be 4 times a year times 12 years. That's 48. So now we can fill in the blanks. We know R, we know I, we know N. So we've got 1,500 times this stuff. Like I did before, I'll go ahead and enclose the top of this thing in parentheses because I would type it all in at once in my calculator. So 1.025 to the negative 48. Again, make sure to note that. I also need to close those parentheses in the back. All right, then divide that whole thing by I. All right, so we smash through the arithmetic that would be necessary in order to work this out, and what I ended up getting was $41,659.73. So that's actually not bad, because if you think about it, 48 payments of $1,500 is going to amount to a fair amount more than this. So the fact that we're letting interest build on it initially is really helping us out. So that's what we got right there. All right, so one example down. The next example listed in the notes file talks about using Excel to do this. I've already kind of shunted off some Excel stuff until later. I'm doing that again. As I said, there will be one video with all of the Excel stuff for section 6.3 through 6.5 hovering around in it. So keep an eye out for that. You'll see when it's coming. I am going to task you in the assignment. You don't necessarily need Excel. You can use the formula just fine. And for that particular example, it's annual compounding and payments. So The I is just the interest rate, and N is just how many years you're working with. So look for that in an assignment problem for this section. Okay, so next, we kind of twist things around a bit. So somebody sells a piece of property. They have, a certain amount of money. In this instance, they have $90,000, and they're wanting to figure out how much they're actually going to get out of it based on how they're going to put it into an annuity. So instead of being given an R, we want to figure out the R that goes along with an A sub n of 90,000. Okay, so it's being put in. The interest rate is 4.8% with monthly compounding. So 0.048 divided by 12, that gives me 0.004 when I do 0.048 divided by 12. Okay? And then when I work out N, it's 12 months in a year times a 6-year time span this investment's happening over per our notes. So we have 72 months worth of payments, and we know this guy, he goes right there. So 90,000 is on the left-hand side. We don't know R. That's what we're after. But we know all the stuff on the interior now. So we're going to have 1 minus 1.004 to the negative 72. And then we divide that guy by another 0.004. Okay? So now, again, like we saw in the last section, this is a number. It's not a pretty number, but it's a number. We can work it out. So we have 90,000 equals R times a number. To get R by itself, we just divide that thing over. So let's see here. I'm wanting to keep the formula, so you got to go. All right, so the R value I came up with was approximately 14.41 and 11 cents after you divide both sides of this equation by the stuff you get out of there in the bracket. So yeah, that's totally how I would do this. I'd work out everything in these brackets, get a number, divide 90,000 by that number. Again, as I said before, I am very wary of rounding unless I absolutely have to. So yeah, I kept this exactly in all of its ugliness in the calculator and then just did like a divide by last answer thing. Okay, so one more example I want to take a look at. And I said I wanted to keep the formula up there. It's probably going to have to go because, so for what it's worth, you remember Kate from, the stuff in section 6.3? Yeah, Kate's back at it. So she's, putting away some money. She's set up exactly how quickly it's going to come out over time, and we want to know how long it takes to bleed out, essentially. So in this instance, we've got an A sub n. She puts away 50 grand. So A sub n is 50,000. The payments she's expecting to come out of it are $4,000. This is a college education account, so coming out $4 grand a semester. Okay, that's fair. It says at the end of each quarter. My apologies. So we're given an interest rate. It's coming out at the end of each quarter, and we want to know exactly how many quarters worth of money Kate or Kate's child or whatever. You get the idea. So we're given an interest rate of 6%, so 0.06, and again, we've got to divide that by 4 quarters that would happen in a year. So I is 0.015, and so now we don't know N. So we have 50,000 equals 4,000, and I'm trying to write this over so I've got a little bit of space to work with, and you'll see why in a moment. So, and we've got the negative N baked into that guy. Close my parentheses up top. So, all right. So, short on board space, I'm going to do this as compactly as I can. I need to get the exponential by itself, just like we saw with Kate's, problem from before. So, divide both sides of my equation by 4,000. That goes poof. I've got 4,000 here. multiply both sides of my equation by the 0.015. So I'm short on space to put it over there, but so now I've dealt with that. Okay. So at this stage, now I've got, if I work out the arithmetic over here, so I got 0.1875 equals 1 minus 1.015 to the negative n. All right, so surprise, surprise, minus 1 to cancel. The minus hangs around. Don't lose that guy. So I need a minus 1 right there. That's not a to the minus first. That's bugging me the way I've got that written. But it's 0.1875 minus 1, so you'll get negative stuff. Then divide both sides by negative 1 after you've worked that out, and you'll have 0.8125. I skipped over a digit, so it's 0.8125 equals 1.015 to the negative n. All right, hopefully you remember this deal. Now we take a log. And through the magic of jump cuts, I have the next step written. So to get n by itself here, we got to get it out of the exponent. We apply a natural logarithm to both sides. As before, base 10 is fine if you prefer. ln left-hand side equals ln right-hand side. Our properties of logs say I can take this exponent, and he comes out front. So I have negative n times this natural logarithm. Now I just have to get n by itself. So we have ln 0.8125 divided by negative natural log of 1.015. Again, if you have the minus somewhere else, that's fine. If you do it in 2 stages, also fine. But we're short on time. This video is about to get cut off. So we work this out. I got 13.95. So it's going to take 14 quarters in order for Kate's investment to bleed out completely. So it's about 3.5 years worth of academic time. Here's hoping it works out. All right, so that's ordinary annuities. I want to talk about a couple of different tweaks on this setup in the next video. So keep watching. Go get a sandwich, whatever.